Welcome to this discussion on cubes. Here we shall spend some time to understand the basic concepts regarding cubes and then focus our discussion on situations involving cutting of cubes, which is a favorite area of aptitude test setters. We have seen that many students keep away from cube-based questions in aptitude tests. It is either because they feel that cube-related questions are very difficult and beyond their grasp, or because they find it difficult to visualize the given situation. We shall try to eliminate both these issues through this discussion. Questions from cubes appear in aptitude test papers because they help test setters to assess a candidate's ability to visualize and the capability to follow the instructions systematically. Once you have a clear understanding of the basics and a good foundation, questions from this topic can be handled with ease. Let us get started towards this. Look at the cube given in the slide. We can see that a cube is a three-dimensional object bounded by 6 equal squares. The angle between any two adjacent faces is a right angle or 90 degree. A cube has 6 faces. Each of these 6 faces is a square. We have 3 pairs of parallel faces in a cube. In the figure, the front and back faces are indicated as 1 and 2. They are parallel. The faces indicated as 3 and 4 are the top and bottom faces. Those two are parallel. Faces 5 and 6 indicated in the diagram are the two side faces. They are also parallel. Please observe that the front and back faces are perpendicular to the top and bottom faces and the side faces. The top and bottom faces are perpendicular to the side faces. The cube has 12 edges, 4 along the front face, 4 edges along the back face, and 4 edges along the sides. Every cube has 8 corners. Thus, a cube has 8 corners, 12 edges, and 6 faces. Further, at every corner of a cube, the 3 adjacent faces are mutually perpendicular. In many cube-related problems, we might come across situations involving painting of the cube faces. In such situations, we need to calculate the total surface area that need to be painted. Since the surface of the cube comprises of 6 square faces, the total surface area is 6 times a square, where a is the length of one side of the square. Many a time, we would require finding the volume of a cube. Volume of a cube of side a units is given by a cube. It will be very helpful if you can memorize the cubes of some numbers. 1 cube equals 1, 2 cube equals 8, 3 cube equals 27, 4 cube equals 64, 5 cube equals 125, 6 cube equals 216, 7 cube equals 343, 8 cube equals 512, 9 cube equals 729, 10 cube equals 1000, 11 cube equals 1331, 12 cube equals 1728. Now that we have seen the basics of the cube, let us see some problems that can come from this section. These questions will help you develop the ability to visualize. We can classify the aptitude questions that usually come from cubes into three categories. 1. Problems related to cutting a cube into cuboids. 2. Problems related to painting a cube. And 3. Miscellaneous cube-related problems. We shall restrict this discussion towards questions involving cutting of cubes. Let us look at the question Q1 given in the slide. A cube of side 10 cm is cut into two equal cuboids by cutting parallel to a face. What is the increase in total surface area because of the cut? In problems related to cubes, you should understand the given situation clearly before you set off. Here we are cutting a cube of side 10 centimeters. That is, each side of the cube is 10 centimeters in length into two equal cuboids. A cuboid is nothing but a rectangular prism. Each side of a cuboid will be a rectangle or a square. The cube and the cuboids obtained after cutting are shown in the figure. The two newly created faces are shown in yellow. We can see that they are also squares with length of side 10 centimeters. The area of each of these new squares equals 10 centimeter into 10 centimeter, which is 100 square centimeters. As two such squares are created as a result of cutting, the newly created surface area is 200 square centimeters. Now please read the question Q2. Before we move to solve this problem, let us understand the problem clearly and look at what is required in a step-by-step manner. We have a solid cube with us. We are allowed to make 3 cuts on a cube. That is, we can cut 3 times. We need cuboids as a result of cutting. That is, all the pieces that we get should be cuboids or rectangular prisms. We saw earlier that a cuboid or a rectangular prism is a 3-dimensional object with all the faces either as rectangles or squares or a combination of these. The adjacent faces of a cuboid are mutually perpendicular. Opposite faces are parallel and equal. We are not allowed to rearrange the cut pieces. That is, during the cutting process, we should not move, remove, or stack the individual pieces. If we want all the pieces obtained by cutting a cube to be cuboids, we should be cutting parallel to a face of the cube. If we cut obliquely, we will not get cuboids. The figure shows the situation when we cut a cube parallel to a face once. Because of this cut, we get 2 cuboids. Here we can see that if we make 2 cuts parallel to a face, then we get 3 cuboids. If we make 3 cuts parallel to a face, then we get 4 cuboids. Or in general, if we make n cuts parallel to a face, we will get n plus 1 pieces. The question posted to us is, what is the maximum number of cuboids obtained by making 3 cuts on the solid cube when we are not allowed to rearrange the cut pieces? We saw that if we make 3 cuts parallel to the same face, we get 4 cuboids. Is 4 cuboids the maximum? Let us try a different approach. Earlier we made all the 3 cuts parallel to the same face. Now let us make 2 cuts parallel to the side face and 1 cut parallel to the top face. We get a total of 6 cuboids as a result of this. If you observe the process carefully, the first 2 cuts that we made parallel to the side faces gave us 2 plus 1 or 3 cuboids. The third cut that we make is parallel to the top face. Note that this cut is perpendicular to the previous 2 cuts. This third cut cuts through all the 3 cuboids that we obtained as a result of the earlier 2 cuts and cuts each of those into 2 pieces. Thus, we have 3 into 2 equals 6 cuboids. Now we have more number of cuboids than the previous case when we made all the cuts parallel to the same face. Let us try out another option. We shall make the first cut parallel to the side face, the second cut parallel to the top face, and the third cut parallel to the front face. We can see that all these cuts are mutually perpendicular. The first cut cuts the cube into 2 cuboids. The second cut cuts through both these cuboids, cutting each cuboid into 2 pieces. Thus, we have 2 into 2, 4 cuboids now. See the 4 cuboids extending backwards. Then we make the third cut parallel to the front face. Note that this third cut is perpendicular to both the previous cuts. Thus, it cuts through all the 4 cuboids obtained as a result of the previous 2 cuts. Thus, we have 4 into 2 equals 8 cuboids. This is the maximum that we can get as a result of 3 cuts. If we make all the cuts along the center, the resulting cuboids that we get will all be identical, and in this case, it will be cubes as seen in the slide. A few observations from the previous problem would help us tackle similar problems better. Firstly, if we want cuboids as a result of cutting the cube, then we must make the cuts parallel to the faces. If we make n cuts parallel to a face, we get n plus 1 pieces. When we made 1 cut parallel to a face, we got 2 pieces. When we made 2 cuts parallel to a face, we got 3 pieces. When we made 3 cuts parallel to the same face, we got 3 plus 1, 4 pieces. If we cut along 2 perpendicular directions, we can multiply the number of pieces to get the total number of pieces. For example, when we made 2 cuts along one direction and 1 cut along a direction perpendicular to the 2 cuts, we got 2 plus 1 into 1 plus 1, which is 3 into 2 equals 6 cuboids. When we made 1 cut along one direction, second cut along a direction perpendicular to the first cut, and the third cut in a direction perpendicular to both the previous cuts, we got 1 plus 1 into 1 plus 1 into 1 plus 1 equals 8 cuboids. The maximum number of pieces is obtained when we distribute the cuts as equally as possible along the 3 perpendicular directions. When we made all the 3 cuts in the same direction, we got 4 pieces. When we made the cuts as 2 cuts and 1 cut along 2 different directions, we got 3 into 2 equals 6 cuboids. When we made the 3 cuts as 1 cut and 1 cut along 3 perpendicular directions, we got 2 into 2 into 2, or 8 cuboids, the maximum. Now look at question Q3. What is the maximum number of identical cuboids that can be obtained by making 6 cuts on a solid cube if you are not allowed to rearrange the cut pieces? We can apply the learning that we had from question Q2 while approaching this question. From the observations we made, we can say that if we want to maximize the number of cuboids when we are not allowed to rearrange the cut pieces, we should distribute the cuts as equally as possible along the 3 perpendicular directions. Here we are allowed to make 6 cuts. When we divide the 6 cuts equally along the 3 perpendicular directions, we would make 2 cuts each along each of the 3 perpendicular directions. As it is mentioned that we need identical cuboids, the cuts should be equally spaced as shown in the figure. The 2 cuts, cuts 1 and 2, are parallel to the side faces. Cuts 3 and 4 are parallel to the top and bottom faces. Cuts 5 and 6 are parallel to the front and back faces. 2 cuts along a direction would give 2 plus 1 or 3 pieces. Since we are making 2 cuts along the 3 perpendicular directions, as we have seen earlier, the total number of pieces obtained will be the product of number of pieces obtained in each direction. Thus, we will get 2 plus 1 into 2 plus 1 into 2 plus 1, which is 3 into 3 into 3, 27 cuboids. In this particular case, these 27 cuboids turn out to be cubes as we are making same number of cuts along each of the 3 directions and the cuts are equally spaced. Let us go through this once again. Cuts 1 and 2 are parallel to the side faces. Those give us 2 plus 1 or 3 pieces. Cuts 3 and 4 are parallel to the top and bottom faces. Those are perpendicular to the first 2 cuts. As such, they will cut through each of the 3 pieces obtained from the previous cuts and cut each of those into 2 plus 1 equal 3 pieces. Thus, after 4 cuts, that is 2 cuts parallel to side faces and 2 cuts parallel to the top and bottom faces, we will have 3 into 3, 9 cuboids. In the figure, you can see that these 9 cuboids extend backwards. Now we make the next 2 cuts, cuts 5 and 6, parallel to the front and back faces. Observe that these 2 cuts are perpendicular to the cuts 1, 2, 3 and 4 made earlier. So these 2 cuts will cut through each of the 9 cuboids obtained as a result of the previous cuts. Moreover, they will cut each of these cuboids into 3 pieces. So we have a total of 3 into 9, 27 cubes. Now let us look at a slightly different situation. Read question Q4. The situation is quite similar to the earlier ones. We have to cut a solid cube into identical cuboids. We need to get the maximum possible number of cuboids. We are not allowed to rearrange the cut pieces. We can make 14 cuts. The difference, however, is the peculiarity of the number 14 when compared to 3 and 6 we looked at earlier. Let us look at this systematically. From our experience with earlier situations, we know that the maximum number of cuboids are obtained when we distribute the cuts as equally as possible along the three perpendicular directions. In this problem, we are allowed to make 14 cuts. So for getting maximum cuboids, we should distribute these 14 along three directions. But 14 is not exactly divisible by 3. We cannot have 14 by 3, which is 4.67 cuts along a direction. The best possible equitable distribution of 14 along three directions would be as 5, 5 and 4. We know that n cuts along a direction would yield n plus 1 pieces. So the 5, 5 and 4 cuts would give 6, 6 and 5 pieces. Moreover, since these cuts are in mutually perpendicular directions, each of these cuts will cut through the cuboids obtained by cutting in other directions. So the total number of cuboids obtained can be got by multiplying 6, 6 and 5. So we will get 6 times 6 times 5 or 180 cuboids. Now let us look at one last question before we stop. Till now, we looked at problems where we were not allowed to rearrange the cut pieces. Let us see what happens if we are allowed to rearrange the cut pieces. Look at this question. What is the maximum number of identical cuboids that can be obtained by making 6 cuts on a solid cube if you are allowed to rearrange the cut pieces? The wording of this problem is very similar to Q3 that we did earlier, except that here we are allowed to rearrange the cut pieces. When we are not allowed to rearrange the cut pieces, the maximum number of cuboids will be obtained when we distribute the cuts equally along the three directions. I hope you would remember that the maximum number of cuboids we got there was 3 times 3 times 3 or 27 cuboids. However, when we are allowed to rearrange the cut pieces, we take a totally different approach. The method we follow is cut the cube into 2 using the first cut. We get 2 pieces. Take the 2 cut pieces. Keep them one on top of the other. Make the second cut. We get 4 pieces. Take the 4 pieces. Keep all of them one on top of the other. Make the third cut. We get 8 pieces. I hope you are able to visualize the process. Take these 8 pieces. Keep them stacked one on top of the other. Make the fourth cut. We get 16 pieces. Take all the 16 pieces. Keep them stacked one on top of the other. Make the fifth cut. We get 32 pieces. Take all the 32 pieces. Keep them stacked one on top of the other. Make the final sixth cut. We get 64 pieces. We can see that the number of cuboids obtained when we are allowed to rearrange the cut pieces, 64, is much larger than the number of cuboids obtained when we are not allowed to rearrange the cut pieces, which was 27. Again observe that 64 is nothing but 2 raised to 6, where 6 is the number of cuts. In general, when we are allowed to rearrange the cut pieces, the number of cuboids we get is 2 raised to n, where n is the number of cuts. In this discussion, we looked at the basics of a cube and did various problems involving cutting of cube into pieces. It is important that while doing problems on cubes, you try to visualize the situation. If possible, draw a rough figure and indicate your thoughts on paper. Once you look at 10 to 15 variations of cube-related questions, you will be able to tackle all questions coming from this section. Thank you.